Yes, so let us start the session.
Yes,
Yeah,
sir.
Okay, I will introduce first. Yes. Good morning, all. So, I am Professor Vaishali Khandwe, tech privileged to introduce our today's session speaker, Dr. Prasanta Panigrahi. He is professor in Department of Physical Sciences at IISER Kolkata. He completed his PhD from University of Rochester, New York, USA in 1988. He completed his postdoctoral fellow from University of Illinois at Chicago from USA in 1990. He also completed again postdoctoral fellow from University of Montreal, Canada in 1993. SIRS has research interest in quantum computation, quantum information, physics of cold atoms and molecules, nonlinear dynamics, quantum field theory, and wavelet transform. Sir also published many research papers. Now, Prasanta Panigrahi is a professor at Indian Institute of Science, Education and Research, Kolkata, in the Department of Physical Sciences, and has also served in the faculty of University of Hyderabad and Physical Research Laboratory earlier. He is the principal investigator in the prestigious project Quantum Information Technology with Photonic Device under the Quantum Enabled Science and Technology at Interdisciplinary Science Cyber Physical System Program of the Department of Science and Technology. He is an international project evaluator for the Austrian Science Fund, Swiss National Science Foundation, Science Academy of Science, National Research and Development Agency, and National Project Evaluator for ACRB, BRNS, DST, Indo-US Science and Technology Forum, and also Homi Baba Fellowship Council. He is a referee for many peer-reviewed journal like Physical Review Letters, Physical Review, Journal of Physics, Pattern Recognition Letters, Physics Letter, then Physics Letter, amongst many others. He is in the editorial boards of Prize, Students' Journal of Physics, Physics Education, District Dynamics in Nature and Society, also Journal of Quantum Information Science and Atoms. He is also a fellow of National Academy of Science, India. So today we have a great eminent personality with us, that is Dr. Prasanta Panigrahi. Welcome you, sir.
Sir, your audio is mute. Sir, unmute yourself. Sir, your audio is mute. Okay, there may be some technical issue at the end. Just wait.
unmute yourself, sir.
No. Sir, can you unmute yourself? Kate sir, try to unmute him.
No,
Yeah.
sir. Oh,
Is it
yes.
okay?
Yeah.
Yes, yes.
Now I go back. Are you sharing the screen? Okay. This one, right? Yeah. Enter screen. Click, share. Okay. Am I audible now?
Yes, sir.
Yes, sir.
Okay. So thank you. Thank you for your kind words. And first of all, I must say that it's quite nice to see so much of enthusiasm in this new upcoming area, quantum computing. And today I'll be concentrating on algorithms. And it's thanks to the initiative of AICTE, I do see a lot of interest in training faculty to take this area forward to the students of India. This is a very unique opportunity. Now, as was mentioned by ma'am, we all started our life, like in field theory and hardcore physics problems. But since starting from 90s, I'll tell you why. Again, because of certain algorithms, quantum computing has slowly emerged as the area which is mostly researched by many people, starting from mathematics to computer science to engineers. So quantum computer is the reality. So it has really caught the fancy of the world, and hopefully tremendous amount of technology is going to come out of it. But amazing thing is that as we all discovered with very many advanced courses, this physics part is fairly simple. It involves very basic things about quantum mechanics. Of course, the experimental part is difficult because of you need low temperature, very accurate experimental facilities. So experimental part is not very easy. Theory part, I would realize that it's fairly simple. You can actually contribute quite a bit sitting from here. But to our good luck, particularly for the Indians, there are quantum computational facilities available. There are simulators and real quantum computers. IBM has provided you, so you can sit right here and do. Keeping that in mind, I'll slowly introduce you first to the principles that underlies quantum computing, then get into algorithms. Keep in mind that algorithm is a simple byproduct. So principles of quantum mechanics, once it is clear, algorithms will follow. So now that is the reason why. Yeah. Hello, am I audible?
Yes, sir, you are audible, sir.
Yeah, okay, very good. So now, I am going slowly. So I'll tell you first brief introduction about this quantum computing. It will have, both development, some history part, and why we are doing it. What are the basic ideas that get into quantum computing, namely superposition and entanglement? Although very many different kind of correlations are slowly manifesting and are being used, like for example, quantum discord and the quantum steering, you will find out still superposition and entanglement are the key principles. Now, quantum mechanics has restrictions, because of which when you are thinking about some algorithm, you have to keep those things in mind. Classic one being so-called no cloning theorem. In plain English words, it means you cannot Xerox. You cannot clone a quantum file. You cannot Xerox a quantum file. Now, for example, what are the machines which people are coming up with? You will find out the machines which people are designing, there are two varieties. One depends on so-called gate, which is the architecture is pretty much like our computers what we have right now these days, except at the point where there is a node where you put in something like a 0 or 1, which physically means applying no voltage or applying 1 unit of voltage in a circuit, you put a quantum state. That design is very much like our classical chips extended to a quantum domain. There is another kind of quantum computer which has been realized starting from the so-called D waves. You can do a bit of searching while I am talking. That depends on annealing. What is this thing? It is a bit new. I'll tell you about that. Now I'm talking about algorithms. So very many algorithms which are available in the market, starting from this Deutsch-Dosa DJ algorithm. That is the first one. And then of course I have picked up Bernstein and Bhajirani, because Bhajirani got his education from IIT Bombay. He is a product of Maharashtra. Now Grover is of course from India, and I'll point out Grover's algorithm, and on quite a few other things which are now in the market, which people are using for solving physical problems. But keep in mind, once the principle is clear, the rest will follow. So be patient. Of course, in a 1 or 2 talks, you will not get all the ideas, but go slow, interact with people, pick up some problem, and you will be able to learn quantum computation in due time. Now, what is a quantum computer? So it's a quantum computer is a device which makes use of principles of quantum mechanics. Now, principles of quantum mechanics that manifest when you go to the subatomic particles, like for example, at the level of molecules, atoms. Now, quantum principles manifest. That is how we discovered quantum mechanics, because we found that the physical laws at a bigger scale are explained by Newton's law, 3 of them. There is a dynamical equation, and there are these principles of inertia, action and reaction, which governs the physical world. But as you looked at atoms, molecules, it was very clear that the rules there are different. And slowly, through experimentation, people found that the so-called Heisenberg's matrix mechanics or Schrödinger's wave mechanics governs the dynamics. There's the equation called Schrödinger's equation. which essentially tells you how the system develops in time. As time went along, people found out what the connection between the quantum world and classical world. Essentially, what you have to do is take something like an expectation value. Those are physical quantities. For example, if you want to find out the energy, take the expectation value of the energy, and you do find that energies are quantized, like in hydrogen atom. Then you try to find out the underlying law. Underlying law is that there is a Schrodinger equation. You have to find out and solve the wave function. Wave function has all the information, and informations are extracted by measurement, and measurement is done through operators. But those are all simple matrix behavior or differential equation which we have solved starting from Newton's equation. But what is it that uniquely quantum? Uniquely quantum is quantum measurement. As I go along, I'll emphasize that point, that quantum measurement. What people found that the moment you measure, the state collapses. So measurement or trying to see the system affects the system, which is very different from the classical world. Classical world, you can measure the length, you can measure the height, nothing happens. The object remains like that. Measurement apparatus do not change the state of the observed object. In quantum mechanics, is very different. Quantum mechanics, the moment you measure, the state changes. So that is the key principle which guides, for example, that if you are developing certain, like quantum key distribution, certain quantum cryptography applications, you will find out it is built on this principle. That if somebody else like Eve tries to see through measurement, then the state is going to change. And once we know the state is changing, we know that there is somebody called Eve is trying to see what is written there. So this aspect, please keep in mind. Everything you can do starting from matrices, as Heisenberg discovered long time back, 25, 26. Nothing much has changed in quantum mechanics. If you take a matrix, you know how to find out its eigenvalues, eigenvectors, the expectation values. Those are all behaviors which we learned in our starting from school, college days. Same mathematics apply here. We have not gone beyond that, 2 by 2 matrices, and bit more than 2 by 2. But what is new is this measurement. Measurement leads to collapse of the state. That if you ask non-physics people have difficulty. Therefore, I am telling, and that gives the power that quantum mechanics or quantum computer derives. It has unique, applicational aspects which I will emphasize as I go along. Now, so when you talk about superposition, what is superposition also manifests in nature. For example, you take light, electric field, for example, you can superpose. If there's the electric field, two of them, E1 plus E2, for example, in linear theories like Maxwell equation or Schrodinger equation, you can superpose. If U1 is a solution, E2 is a solution, alpha U1 plus beta E2 is a solution. That we have seen in Maxwell equation, because Maxwell equation is linear. Same principle applies to Schrodinger equation. Schrodinger equation is also linear. So if you really, since you all are faculty members, whatever you have learned in Maxwell equation, same mathematics apply here. Green's function, solving differential equation, right? And only thing that changes is boundary condition. Here, square integrable. Psi mod square is normalized to 1. Physical interpretation. It means that the probability of finding a particle is 1. You can find the particle somewhere in the whole world. So that is the so-called L2 function, psi mod square dx integration is equal to 1. So the boundary condition, so this kind of conditions, additional conditions come in. Otherwise, when you solve the equation, the same equation, Laplace equation, Poisson equation, and whatever you have learned in electromagnetism, same methods you use. Sometimes sine, cosine. For example, you must have seen in a resonator, you solved the problem, you got sine and cosine, you demanded a boundary condition that tangential component of the electric field should be continuous, normal component should vanish. Same conditions. Quantization, like n is quantized in a resonator, not all modes are allowed, gives rise to quantization condition in particle mechanics also. You get particle in a box, energy quantized, it is proportional to n square because of the same principle. What the difference? Difference is square integrability. The wave function mod square is equal to 1. Electric field, sometimes you do put that condition, sometimes you don't. You have a Maxwell equation which finally boils down to wave equations, you solve it, or for example, Laplace equation, Poisson equation, same method applied here. Green's function, same method. Again, superposition interference you have seen there, same superposition interference follows here. So now, this entanglement is something new. So earlier I pointed out, measurement is something new. Measurement is something unique to quantum, which is not there in the classical world. You have not seen it in the electromagnetism area. Electromagnetism, whatever mathematics you learn there, same mathematics follows, except measurement. Now I am telling you another concept called entanglement, which is also not there in electromagnetism. In some sense, it is there. If some of you are careful, when you look at superposition, you have another degree of freedom called polarization. So the polarization, electric field is a vector. The vector part is polarization. Linearly polarized, circularly polarized. That information is there. In addition, you have a field which is a function of x and t. It could be sine, it could be cosine, those kind of things, or exponential. So this structure, for example, when you take two electric fields and superpose, you have polarization times a function. Function describes the behavior of the electric field in space and time. The polarization, which is a unit vector typically, tells you the state of polarization. Is it circular? Is it linear? And you will have two of them superposed. Entanglement also comes in there. It's an amazing thing which people are getting clarified now. So the so-called classical entanglement is the word which has now come because of electromagnetism. So only thing keep in mind that is unique to quantum mechanics is measurement. Measurement leads to collapse of the state. Therefore, intrinsically it affects the state. And that is the thing which is being used. And that's the thing which creates maximum confusion. If the measurement leads to collapse of the state, and it is quite random, you will see, then what can you do with it? And that is where the power of quantum computer comes in, that in fact you can actually use that to your advantage. So as we go along, this aspect, please keep in mind. Now, why you need quantum computers? You will see that in 90s, I was referring to 90s, these two gentlemen, Shor and Grover, they pointed out that certain things you can do much faster. For example, Shor pointed out, Peter Shor is a computer scientist and a mathematician, that factorization you can do much faster. Now, why it's so big deal about factorization? Because factorization and related algorithms are useful for our secretly sending messages, namely cryptography. So factorization people use as a popular example, but similar kind of things where multiplication is easy, finding factors is difficult. So these are like one-way functions. So if, for example, Alice and Bob, they are friends, they have two numbers which they want to use as a code, they can multiply it, get a big number, use that as their key. They can send messages using that as a key. What is the meaning of using that as a key? For example, all our language A, B, C, D, E, F, G, we can convert into numbers 1, 2, 3, 4, 5, 6. So whatever you are sending, you can convert them into some numbers. That number can be added to the key and be sent. Since both of them know the key, they can subtract the key, which is typically a multiplication like 5 times 3, get that number. Now having access and knowing that individual keys and 5 and 3, they can actually decipher the message. So therefore, it's a very simple example. 5 and 3, two of them, they meet, Alice and Bob, decide that they will use a big number. That big number is a multiplication of two small integers like 5 and 3. And that big number is used as a key. It is added to all the messages. Once message comes in, you can actually factorize, get your component of the message. So this is in a very simple way, how cryptography occurs. Therefore, if you can factorize, then you can actually, why is it difficult for somebody else called Eve to decipher? Because if she only knows the big number and its component, like 15 is 5 times 3, she can decipher the messages. But for that, she has to take a big number, 15 is a very simple example, and find out its components, the ones which have been multiplied. That takes a lot of time. So multiplication is easy, finding factor is difficult. These are called one-way functions. These are the typical examples which is used in cryptography world. So Shor pointed out that in principle, this huge amount of time that is being taken to solve this problem can be done in a polynomial time, and that actually immediately woke up the people who are into banking, into secret sending of messages to come up with a better way, and they poured money into quantum computation so that quantum computers can be designed first with two goals. First, to find out the secret messages being sent by your enemies. Second, to come up with better way of sending computation, secure messages. So both the goals are there. And Grover, for example, showed a much better application that if you have a big library, you are looking for a book. Typically, if you do a search algorithm right now, which you use in Google, it will take large amount of time. You can actually do it much faster, and that uses superposition principle, like parallel processing. And it's very simple to see. For example, you can take simple matrix examples, and you did convince yourself that you can do it much faster. So basically, these are the two things that Grover's search and source factorization in 90s that brought quantum computation to mainstream. You will find out before that, 80s, certain developments were there. I'll emphasize to you once we go along. People like Richard Feynman in 80s were pointing out that if you want to solve big problem, which is quantum in nature, like for example, finding out confinement in why quarks are confined in a proton, which is still unsolved problem called confinement. It's a quantum problem. Classical computers will have difficulty. You should use quantum. That was Richard Feynman in 1982. So let me summarize here. Quantum mechanics was known and has been, thoroughly worked out since 1925-26. There's a book by Paul Adrian Dirac, 1932, which basically has all the things what we know. If you read that book, you will know everything. There's nothing more. So there is a difference between quantum world and and the world of the classical thing. The method that is used to solve is pretty much similar, matrices and differential equations. We know, for example, from linear algebra, matrix behavior, that was Heisenberg, matrix mechanics. We know from electromagnetism how to solve Maxwell equation, similar kind of behavior for Schrodinger equation. The difference are twofold. One is wave functions are square integrable. Superposition was known wave mechanics, same thing applies here. There is entanglement. If there are more than 2 degrees of freedom or two particles, one or two more than two, similarly degrees of freedom, polarization and spatial component of the electric field, you can entangle them. Entangle means non-separable. So that was there, which is now being called as classical entanglement in electromagnetism, extends very much into quantum world, which is finding application. There is a subtle difference between the so-called classical entanglement and quantum entanglement. As I'll go along, I'll emphasize to you. But unique thing is measurement. Measurement leads to collapse of the state. That does not happen in the classical world. Now, as usual, certain problems, particularly algorithms, since I'm talking about it, is the one which brought all the people like mathematicians, computer scientists, and physicists into one forum. Whole goal is to find a quantum computer and use it for solving practical problems. To start with, cryptography. One of the main reason is cryptography. Okay, so now, as I told you, let me tell you a little bit history about this timeline. See, quantum mechanics was pretty much developed by 1925-26. There are, debates going on about, what is the basic principle of quantum mechanics? Is it complete? EPR paper, you might have heard, Einstein, Podolsky, Rosen, 1935, pointed out quantum mechanics is not complete, and people have not accepted it. That, this measurement led to collapse. That somehow didn't appeal to Einstein. So God doesn't play with dice. What is famous words? Now, debate continued. Lot of developments, like for example, Feynman was involved in quantum electrodynamics that explained the interaction of charged particles. the quantum theory. But debate never stopped. It was John Bell, who in 60s pointed out that take those same wave functions, take operators, now product of operators. So through that, he came up with an analogy between classical world. What was the analogy? The analogy was that take random variables, like for example, yes, no, coin tossing. So now take two particles, Alice and Bob. If they are governed by coin tossing, you refer to the res output as plus and minus. You can convince yourself if two parties are simultaneously taking values, it could be plus plus, plus minus, minus plus, minus minus. Now they took in a combination of 4 ways of doing it. So independently, some 3 kind of observations and minus 1. It was taken because it has a very nice quantum analog. So quantum mechanically, it was a wave function, 2 particle wave function, product of 2 operators, typically polymatrices, as you might have been familiar, and 4 terms, 3 positive, 1 negative. That combination was, due to John Bell. He in fact took this idea from a work of Bull, B-U-L-L, a statistics person who had thought about this kind of observations in classical statistics. 1887 or 1885, long time back. The quantum translation of that by John Bell with wave functions which are entangled, which are very well known now as Bell states, he found that it will be 2 root 2 and minus root 2 root 2. This expectation values of product of 2 operators, and there are 4 terms, superposition. That will lie between 2 root 2 and minus 2 root 2. It was 2 and minus 2. This result was due to Boole. So please take a look at it. If some of you are interested, I will send some papers. You can go through it. It's as simple as that. This observation of, this product of 2 fellows or 2 random statistics in a suitable combination leading to values between 2 and minus 2. Whereas in the quantum world, with entanglement, 2 root 2 to minus root 2 is the one which differentiates classical to quantum. There was a very quantifiable way of testing due to Bell in 60s that led to experiments, and all the time quantum mechanics was correct. And in fact, now those kind of measurements are used to test entanglement. How much of entanglement is there? Which is, by the way, is a very difficult problem to solve beyond 2 particles. So now this is how it has developed. So these are the, for example, Feynman and de Broglie. So de Broglie, why am I putting these people? Because he's the person who brought superposition and particle and wave nature. That is what is being used here. This duality, particle and wave, both the aspects you can actually take advantage. Wave is superposition. Particle nature is measurement. The moment you measure, state collapses to a definite point. So those are the 2 aspects which are being used. And it was Feynman who first realized that quantum mechanics is quite mysterious. His point was that, with Richard Feynman telling that nobody understands quantum mechanics, one has to take him seriously. So 82, he pointed out this thing. Very nice paper, IGTP, International Journal of Theoretical Physics paper. I suggest, please take a look at it. That he pointed out that there is, basic laws, although they are similar, second order differential equation, but you can actually create machines using here. And those machines will be very powerful and much more powerful than classical physics simply because of superposition. So-called parallel processing, quantum advantage. That can be used to solve complicated problems. But Feynman was alluding to quantum chromodynamics problem of confinement. Now, and he also suggested how to sort of use these laws to design a computer. But it was David Deuce in 85 who precisely showed that the so-called quantum Turing machine, this is a mistake here, Turing, Q-R-I-N-G. It was, Turing, this British mathematician who is very well known for many things from breaking of this German code. So it was this Turing who came up with the principles of computation. What is the principle? His point was that you can do so-called universal computation using addition of numbers 0 and 1. 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, which is 0. So this mod 2 mathematics using 0 and 1 can be used for universal computation was due to Turing, the so-called Turing machine. Now, for example, how does it manifest in our physical computers? We people like physics people, engineers, we convert 0 to no voltage, 1 to 1 unit of voltage, and 1 plus 1 becoming 0 can be converted in a circuit language. The moment there is a voltage, you put a cutoff kind of thing like 1, if the voltage is above that, output will be 0. So many of you who are engineers or electronics experts, you will immediately realize this can be translated into circuit language. That's what we have done. All the quantum circuits depend on classical circuits, depend on that. Big chips, so much of computation, but basic idea is this: addition, mod, 2. Now you can add, subtract, everything can be done. So then, computer people made it much more complex. They developed gates, and we are now carrying forward. And David Joyce pointed out, if we are talking about the language of gates, there are only 2 gates which are there in quantum computers. As we give you the mathematics, one gate, the so-called Hadamard, produces superposition. The other gate is called control knot, which creates entanglement. And as I pointed out to you, the basic idea of powerful quantum machines is quantum parallelism, parallel processing that comes through this Hadamard gate superposition. Then this quantum entanglement, which is unique to quantum mechanics, and that brings in certain kind of non-locality. I'll emphasize that point here. Those 2 things, you need only 2 gates. And Joyce pointed out, you can design a universal quantum computing machine exactly in parallel to the classical Turing machine, and you can have a circuit which is universal. And that was a unique conclusion. Again, please take a look at it. It is Proceedings of Royal Society, very readable paper. And that, I think, led to the foundation of quantum computers, which we are now realizing, like IBM and others. You will find out whenever you go to any circuit, you will find Hadamard control lot, Hadamard control lot. So now, Shor pointed out, you are essentially using quantum Fourier transform. Fourier transform, you would realize, actually is, in some sense, parallel processing, quantum parallelism. There are many ways. Fourier transform is one way. So you use that to show that large numbers can be factorized in polynomial time. Keep in mind polynomial time. You can have algorithms which are exponential in time. Exponential in time practically means you cannot do it. So therefore, any problem you see in computer science which takes exponential of time, if it can be converted to polynomial time, that means you have achieved something, you have shown quantum supremacy. Now, everybody in the world wants to show that a quantum computer is either superior or inferior or similar to classical one. Big debate going on. So who are playing key roles? Key roles are being played by computer science and mathematics people. They are coming up with big problems which they do not know how to solve. So-called ENP complex problem. If you ask, I am not a great expert on that. And our quantum people are showing, yes, I can do it in a polynomial time. So keep in mind, tomorrow you may be attempting one of those problems. The other great thing is search. Now in nature, search is always present everywhere. Even for example, if you see people are now claiming that in biological things like photosynthesis, when some energy is coming to the, by sun, how it goes to the place where there is a chemical reaction, namely synthesis, photosynthesis. That apparently is done by something keeps similar to Grover. So Grover search is a very simple method where we shows the quantum supremacy, that through the parallel processing, you can actually search things faster. That in library, a book you want to search, quote unquote, is called, and you are looking for things which are not structured, unstructured database. You can show that you can do it much less time, order root n. So goal is to show that quantum can do things faster and of course better. That is where the quantum advantage will come in. So again, let me summarize that the quantum principles allows you a natural generalization, much like the Turing machine, to so-called quantum Turing machine. There is a circuit analog of that as compared to classical ones, where instead of 0 and 1, you put a matrix Simplest being column vectors 1, 0 and 0, 1. So language is numbers becoming matrices. Matrices satisfy vector algebra, superposition, and naturally those are the principles which quantum mechanics is governed by. That was discovered by Heisenberg. So whatever we have learned from matrices comes into play here. Then you can have product matrices, direct product, superposition direct product is so-called tensor product. That gives rise to entanglement. What is entanglement? Non-separability. Now you may ask, in physics, for example, have you seen it? Answer is yes. Simplest example, look helium. In helium, two of the electrons which are there in the ground state, they are actually entangled. So entanglement is a natural concept. Now you have to, if you create superposition and entanglement, you can build a quantum computer. That's what David Joyce pointed out. Now how do you create superposition? It's so-called Hadamard gate. How do you create entanglement? So-called CNOT gate. So those are the two gates through which you don't need anything else. You can create a quantum computer. If you want to build a machine, you have to come up with an idea how to implement the so-called Hadamard and control knot. As you will see, that is what they are doing. So now, many problems you can tackle. I'll emphasize. I'll give you the brief idea about source factorization, Grover's search as we go along towards the end. But do not get worried if you don't understand too much, because I also did not understand in the beginning. And you will find out on your own when you try to understand, you will come up with better things. And the field is still simple, still young. You can bring your own ideas and hopefully do some contribution to this field. Okay. Now, as I told that in a class, the design of a quantum computer relies on the same architecture. And that's what David Joyce pointed out. Except that this mathematics of addition of numbers have to be replaced. Wherever was 0 in a circuit quantum chip, on a classical chip, so you replace that 0 by a vector called 0, ket. This notation is to react, and that stands for a state, which is a column vector, which is 1, 0. Physically, what is it? Electrons of spin. Photons, linear polarization along z direction. A two-level atoms, ground state. There are two states, and one is excited state or down state. So mathematically, if 0 is 1, 0, 1 is 0, 1. You will find out everywhere we do with this thing. And because it is somewhat like 0 or 1, we call them qubit instead of classical bit, which is just pure numbers. Mathematics is multiplication of vectors, addition of vectors, whatever you have learned in vectors, algebra, vectors, scalar product, all those things come here. Mathematics is nothing unknown. But measurement is something which I will emphasize to you, is something which is new. And that actually creates a lot of confusion amongst students and faculty. Now, any system you take, if there are two energy levels, if you can identify clearly, and particularly if they don't talk to others, that means they are free from the environmental interference, you are through. You can design a quantum computer. In IBM, for example, there could be superconducting qubits. Somewhere else, for example, it could be silicon islands talking to each other to extent of light. Some other place, it could be ions, two ions, having two levels, like for example, in a machine which is now available in the market. IonQ is the manufacturer. So these are all two-level systems, quantum systems. Ground state, excited state. Mathematically, 0 is a column vector, 1, 0. 1 is another column vector, 0 and 1. They form vectors that are orthogonal to each other. What is the orthogonality? Like x, y, and z components. Their product is 0. You can check. 1, 0. Then when you take product, you have to obey matrices. This dagger times 1 will be 0. 1, 0 times 0, 1. You have to normalize it. So 1, 0, this dagger is bra, and ket. This notation is due to react, will produce a number. That 0, 0 will be 1, 1, 1 will be 1, 0, 1 is equal to 1, 0 is equal to 0. That is what we have learned from the vectors. Unit vectors I, j, k. I square is equal to 1, j square is equal to 1, k square is equal to 1, I dot j and j dot k dot I is equal to 0. So exactly same mathematics. What we have learned in our vectors. A vector can be expanded in terms of ax times I, a y times j, a z times k. Same thing here. A state can be expanded in terms of 0 and 1. Now, how do you get, for example, AX? You take the vector A, dot E to the I dot A, if you take, you will get AX. Because I dot I is 1, I dot J is equal to 0, I dot K is equal to 0. Same thing applies here. What we learned in our vectors, same thing applies here, nothing big deal. Only thing is measurement. As you see, keep that in mind. I'm emphasizing again and again. Now, physically, where is the state? For example, two-level atoms. In ion, you suitably identify two levels. Electrons are difficult to handle. Now, light is also difficult to handle. Instead, what people do, they take quantum dot. Quantum dot is like a big molecule. There's a ground state and the excited state. Those are, you can handle them. They're stable, they survive for some time, you can handle them. So this is actually a quantum dot in physical quantum computers, or an ion. In ion are pretty much controllable. Superconducting qubits, they're superconducting qubit. So they're actually macroscopic quantum states which are relatively stable. So this is what it is. State 0, state 1, ground and excited state, wherever it is. Could be electron spin, could be light polarization, could be atoms, could be a quantum dot, could be superconducting qubits, could be ions. Identify two levels. As long as they're stable, they don't decay, you can use it for quantum computation. And mathematics is 2x2 matrices, nothing more than that. Okay. So these are the things as I mentioned to you. Superconducting qubits, these IBM machines which are available, which you can access, this up to 16 qubits without paying any money. They have a simulator, you can play around. So superconducting qubits. Quantum dots are slowly coming to market. Hopefully they will be the real object in future. This is already in the market using 20 ions. IonQ has a quantum computer for sale. For example, our MEITI, is our electronics department of Government of India, through Amazon has gotten access to many quantum computers. They are providing to practicing physics people. For example, AICT had an advertisement, you might have seen it. Ion qubits are available up to 20 qubit. Photonic qubits will take some time. They are primarily used for communication. So if China has a big quantum photonic qubit through which they communicate, there's a satellite. India is also trying the same way. So these are essentially for communication, because light moves always with velocity c, which is very fast. So primarily for communication purpose, and they can also communicate between ions. For example, you take two ions, they can talk to each other through photons. Now, for example, night defect in diamond, nitrogen defect in diamond. Of late, it has emerged as a very stable unit for quantum computation, because you can actually realize stable qubit. What does the meaning stable qubit? Because in the environment, they will look at the environment, nothing happens to them. As you know, quantum states are very subtle. The moment they get exposed to high temperature, they're gone. So how to stabilize them is a big problem. Talking about stability, topological qubits have made a name now. Because of topology, you might have seen, you may change a coffee cup into a football, but you will find they will never be identical. Because football is something like a sphere, coffee cup is something like a torus, they will never be identical. Similar kind of things, one can take advantage of. In fact, people are taking advantage of. There are topological insulators, quantum Hall effect states, which provide you states which are stable because of topology. You may change them, this, that, but the basic nature will not change. A sphere, football surface cannot become a torus, namely coffee cup's surface. That aspect is called topology. Now, nuclear magnetic resonance, where the very big machines, for example, Professor Anil Kumar in IISc has trained a lot of people. In Pune, IISER Bhopal, IISER Mohali, you see, you can, if you go to the website, you will find out, including Professor Anil Kumar's, own, that many original ideas were implemented to NMR qubits. They're big machines, but extending them is a problem. You can, in principle, show the applicability of quantum computation. That is what NMR did, but making a big computer out of that is not easy. But all our results came from NMR. Now, let us get a little bit into mathematics. So 0 and 1 is like exactly like vectors. So you have superposition, for example, a vector A is expanded in 3 dimensions as I times X plus J times AY plus K times AZ. Here these are the 2-dimensional vectors, so only 2 of them, the so-called basis, pretty much like your IJK. And it's an unknown state if I do not know alpha beta. So if I want to normalize it, like for example, I square is equal to 1, psi takes a dagger. Dagger is a matrix transpose with star. So that is the one which in quantum mechanics called normalization. Mod psi square is equal to 1. You can check that to give rise to these conditions. There are 4 complex numbers satisfying a condition. So in principle, there are 3 independent variables here because 2 complex numbers having 4 real variables. But there is one condition because of normalization. So in principle, there are 3 which are free. But quantum mechanics has another problem. This state psi or exponential I theta times psi will describe same physics because physics comes only when you take expectation values or measurement. That involves a mod, taking up a mod. In a mod, overall phase doesn't matter. Therefore, one more additional overall phase has to be removed. That's the peculiarity of quantum mechanics. And that leads to only 2 degrees of freedom. So if you take a typical qubit, people only use 2 degrees of freedom. They write as a column vector. So which is like a angle theta and a phase chi. So that comes because of this condition. Now, so this is a typical superposed qubit. This is called an unknown state if I do not know what is alpha beta. And you will show that quantum mechanics will allow you to carry out a lot of things with this unknown state, even if you do not know what is alpha beta. You can send them wherever you want in a quantum circuit, so-called teleportation. Alice will teleport the state to Bob. Bob is in, let us say, in Bombay, from Pune, or any distance you want. Now people have done from particularly China, from Beijing to Vienna. You can teleport a state without knowing it is. The person who gets also would not know, but it is very clear that the state has gone. So this kind of teleportation, dense coding, those kind of things, teleportation particularly, can be done to unknown state, which is uniquely quantum. There is nothing, no classical counterpart. Very good. So this allows for parallel processing. Superposition is parallel processing. All right. So physically, superposition is just addition, 0 plus 1. You see 0 here, 1 here. Now double well potential is an example where ground state is a superposition of both the states. So you might have seen it in Feynman's quantum mechanics book. If you see nitrogen NH3 ammonia has a pyramid structure. There are 2 solutions, and both the fellows are simultaneously possible. The ground state is superposition of these 2 kind of pyramids. That's a simple example which gives rise to superposition of states. So the ammonia molecule continuously oscillates from one state to another. So that's an oscillation kind of thing. 0 to 1, 1 to 0, back and forth. That is called Rabi oscillation. And people, when they find out that kind of oscillation, they do so that it's a 2-level structure. So ammonia, and then Rabi oscillation, and then superposition. State going from 0 to 1, back and forth, back and forth. So very good. So many places, like in the nuclear magnetic resonance, spin states. Now particularly people who are getting into solid state quantum computation, they're using electron spin, and they will tune the electron spin through radio frequency and split the degeneracy through magnetic field. You can actually handle spin up and spin down. If you put a strong magnetic field, electron spin will point out along that direction. You can address them. People are slowly getting into that domain now. Now, entanglement. Historically, it was EPR paper 35, which pointed out that this non-local correlation. Now, what is this non-local correlation? Because of entanglement, that for example, imagine you have a hydrogen molecule, 2 electrons. Of course, this is a very small one. Imagine a much bigger one. What the state again is a 2 electrons. It is molecule, or 2 electrons in helium. Both of them are same. Since you are physics people, or people who have to have some access to quantum mechanics, called a singlet state. Up down minus down up. So one electron is, if it is up, the other flow is down, and the state is superposition, up down minus down up. You may say it looks very peculiar. Up down means if it is up, the other flow is down. Minus down up means if this flow is down, the other flow is up. How is it possible that these kind of things are there? But that is the peculiarity of the quantum world. Superposition is allowed. In a double well potential, if the particle is allowed, like for example ammonia, it can stay in one well or the other. So it keeps on oscillating between this well to other well. Classically, it's not possible. Classically, it will be stuck to one well. How can you imagine that you can go from one to the other? But quantum mechanics, that is allowed. Then there is something called tunneling. If you put some particle in one well, it will tunnel to the other one. So this wave property, superposition, allows this kind of things are possible. Very counterintuitive, but it is true. So then up, down, minus down, up. Imagine you have a big quantum system. That is what Einstein considered in this very famous paper, that one up, down, minus down, up. Up belongs the first particle Alice, second is Bob. So if Alice is up, Bob is down. If Alice is down, Bob is up. Now consider a state where Alice is in Bhubaneswar and Bob is in Pune. What will happen if Alice measures? If Alice finds up state, Bob will be in down state. If Alice finds my measurement outcome is down, Bob will be up. And the collapse takes place instantaneously. That is where Copenhagen interpretation comes into play. There are two terms, the measurement at one end, like Alice or Bob, will lead to the collapse of the state. What is the outcome? Outcome will be completely unknown. It could be up for Alice or down for Alice, 50% probability. But a single measurement will lead to collapse, complete collapse from two terms to one term. If it is up, Alice, Bob will be down. If it is Bob is down, Alice is down, Bob will be up. This is what is called non-local correlation. That really bothered Einstein. How does it happen instantaneously? That the moment and that's why it's non-local. It's not local. You are, here, the moment you measure, other fellow collapses immediately. But since then, a lot of research has gone on, people have found out that although it is non-local, it can happen instantaneously, but information you cannot send faster than light, called causality. So please remember, causality is another principle which comes into play. So causal behavior is not violated. So that way, causality is from relativity. So merging quantum mechanics with relativity has stood the test of time. So you can measure a state will collapse. People have done many experiments. Picture is still true. But through that, you cannot send any information faster than light. Relativity is respected. Causality is respected. So that is the nature of quantum mechanics, and we have to wait. So this is the non-local correlation, because if Alice is in Bhubaneswar, Bob is in Pune, the moment the state collapses to up for Alice, Bob is down. If Alice is down, Bob is up. Now which one? There are two terms. If it is up, down, down, up, and the moment the measurement takes place, a single measurement, immediately state will collapse. To which one? Nobody knows. But if you do large number of measurements, because it is up, down, plus down, up, with a 1 by root 2 factor. Why 1 by root 2? Because normalization has to be 1. Then 1 by root 2 is equal to probability amplitude. Square of that is called probability. 1 by root 2 square is half. Half the time you will find out up, down. Other half will be down, up. It's like tossing up a coin. If it is head and tail, if one measure, one tossing will never tell you which one it is. But large number of tossing will tell you either it is 50% head, 50% tail. Same thing happens here, except that it is classical, that it is probability, here it is probability amplitude. Square of that is observable. So therefore, it is not surprising that this person Bull have come up with these correlated measurements in terms of statistics in 1857 or something like that, which was translated to quantum mechanics language through Bell. So this idea of probability, which statistics people have been dealing with for quite some time, really gave a lot of understanding of quantum mechanics, which is called probabilistic interpretation of quantum mechanics, so-called statistical interpretation of quantum mechanics. That one measurement is random, like Niels Bohr pointed out. collapse of the state. But Born pointed out that if you take large number of measurements, classical picture will emerge. So please convince yourself that this emergence of classical picture from quantum world is a very unique thing. That has puzzled many people. It's still puzzling things now. You can use it for technology. What technology? That this randomness has been used to generate random numbers. You can check a quantum random number generator is actually a technology which is now being sold in the market. Now, why do you need a random number? You need a random number to carry out Monte Carlo simulation, many applications. So quantum principles are found application in generating quantum random number. It's a fast technology which is being sold right now. What the other one? Measurement led to collapse of the state. So it is 1984. It was pointed out by Prasanta, Bennett and Prasanta, that this very simple thing can be used for generating key for secret communication. What is a key? Key is a set of numbers 0, 1, 1, 0, 1, 1. So you can generate a key through measurement outcomes, which is nothing very unusual. You take a state alpha 0 plus beta 1, you keep measuring, sometimes 0, sometimes 1, whatever you get, you put it down, and it's arbitrary. So this thing which you generate is completely random. And one main important thing is, if Eve is seen, Eve will come and try to see, you take psi, how is it? Try to measure, it will lead to collapse. And since you know your basis 0 and 1, Eve doesn't know, so you will find out, I prepare the state in alpha 0 plus beta 1, alpha and beta are 1 by root 2, 1 by root 2. Now what has happened? Somebody must have tinkered because the state is now changed. So this is what was used by Bennett and Prasanta BB84 to generate a cryptographic key which is very secure. That is, now you can check. Actually, many of the experimental things which are being sold now, this QKD84 is a package which is available in the market. So these two things came out of quantum technology so far, very easy, simple measurement leading to collapse of state. And it has only used, this thing about a single particle measurement and no entanglement yet. Quantum random number generation and quantum key distribution. Single particle, only measurement. There, for example, photons have played a key role because easy to communicate with photons, easy to measure like polarizer analyzer, except a bit more short way. So let me emphasize, measurement has played a key role in coming two technologies which are quantum random number generator and quantum key distribution. They only rely on this fact that the state after measurement collapses due to Niels Bohr's, state collapse, the so-called Copenhagen picture. So far, all the experiments have shown that it's completely correct. If you take an unknown state, if the state collapses, completely arbitrarily, it will go from 0 plus 1 to either 0 or 1. So what is this arbitrariness which was hampering the progress now is being useful to generate two technologies. One is quantum key distribution, BB84 being the classic example, other is quantum random number generation. And there is a non-local correlation, as EPR pointed out, Einstein proposed that can be used to do another technology called quantum teleportation. You can actually extend a state create a state from one end, like in Bhubaneswar, and at the end, like Pune, instantaneously. When I say instantaneously, please qualify it, not faster than velocity of light. So again, these two things, which was the key aspects of EPR paper, is being used now. Technology happens because engineers come in, and so far I have used only this superposition, namely interference. Entanglement I have not used. You will see entanglement is very interesting. That leads to teleportation. So very good. Now we are slowly beginning to use quantum mechanics now. Now how does it really look like in measurement type? Measurement type somewhat looks like this. There's the source which will produce entangled photons. Now to create entanglement, you have to be here. For example, if it could be exciton, it could be pi naught, which is produced in nuclear reactors, decaying into two photons. If it is photon, then it is spin up or polarization up, namely along X, This will be along, direction of motion is along Z. It could be left polarized. If it is left, the other pole will be right. If it is right, the other pole will be left. This state which is produced is actually superposition. You may think that how is it possible that it is left, right plus right, left? Answer is that this is unique to quantum. And in fact, you can easily create them. So one goes from here. We started, let us say, in Bhubaneswar, one goes to Pune, one goes to Delhi, and the measurement takes place here in Delhi, here in Pune, and output, if it is like a +1, here the other will be -1. If it is -1, it should be +1. So by looking at correlation measurements, this so-called coincidence measurement, in fact check that outcome is true. This is a typical example which people implement it experimentally. You might have heard, you will see this kind of words: coincidence detectors, entanglement source. Here it is just not entanglement, it is superposition. You can actually take a crystal here, entangle them. So this one represents entanglement. For example, left, left, right, right, or plus, plus, minus, minus. So this kind of notation will come out. You see what is this language? This is state. Now x comma x means product state. For example, 0, 0. What is 0, 0? 1, 0. Direct product is 1, 0. So superposition, the state is normalized to 1. The factor 1 by root 2 comes. And physical, this is amplitude, mod square is the probability. It's a classic example of two photons. Both of them are either in the left. If this pole is left, other is left. Left polarized. Right, right. Or horizontal, vertical. This is horizontal HH, this VB. So what is non-local correlation? If you measure this fellow in Washington or in Delhi, if you find horizontal, a measurement here also will produce horizontal. If it is vertical, it will be vertical. A given measurement will lead to XX or YY. You never know which one. Large number of measurements, half the time XX, half the time YY. That is the probabilistic interpretation of quantum mechanics. Probability amplitude is 1 by 2, mod square is the probability, half. Typically, you will find these kind of experimental apparatus are there, and they are the basics of any quantum computation hardware. Very good. So quantum gates, as I pointed out to you, that there are only two things which was told to us. One is hammered, one is control knot. And you will find out one interesting thing, that everything in quantum we want to do, all the operations, they have to be done by unitary matrices. Because probabilities do not change. Psi dagger psi is 1. Even if you change it, it should still remain 1. Because of it, whatever change you want to do, you have to do through unitary matrices, because they satisfy u dagger u is equal to u dagger is equal to 1. And unitary matrices are exponential of Hermitian matrices. So both the Hermitian and unitary matrices play very key role. Quantum measurements, quantum are done through Hermitian matrices. For example, Hamiltonian, which leads to energy, momentum, angular momentum, they are all Hermitian matrices because they lead to real eigenvalues which are observable. Exponential of that is unitary matrices. Any change you want to do, you want to rotate a wave function, you have to rotate through a unitary matrix. You want to translate, you have to do time translation, whatever you do has to be done through unitary matrices, the probability is conserved. So mathematically, you are dealing with two matrices, unitary and Hermitian. If you understand quantum mechanics very, very well. That. Now, you see, it's very interesting that because it is unitary, whatever you have done in one direction, you can do reverse. Apply U dagger, you will get back to your original state. You see, in some sense, how deterministic it is. That because it is unitary, you can do computation. Whatever you have done, outcome, you can go back and find the original source. That is not possible in a classical computer. So that is what was found in 70s. When they found that when the chip size is becoming smaller and smaller, a lot of heat is being produced. And it was Landauer and then Bennett also found out that this heat is produced because the gates are not reversible. So that this aspect, that the irreversible operation leads to heating and hence loss of information, was a great understanding of 70s due to Landauer and Bennett also from the engineering side. Now, amazingly, you see, they found out that information is heat. Each unit of information lost is half kT amount of energy. You see, energy loss and information got connected. A beautiful understanding of thermodynamics in 70s because of this quantum classical computers chip size becoming smaller and smaller, and it produced a lot of heat, a lot of noise. Earlier, it was not there because chip size was bigger. They used to cool it down, but when the chip size became smaller and smaller, they soon found out that because of this quantum effect coming in, a lot of heating. Mathematically, it was because the matrices or the gates which we are using were non-reversible. You see, that is the point. Lot of beautiful concept of reversibility, reversible behavior because of unitary matrices. Although quantum mechanics is random, because of these unitary matrices, you can reverse it and come back to the original state. They are understood in 70s. And the engineers are always smart. They came up with reversible gates called Toffoli gate, and it was reversible, 3x3 matrices. So they could do really computation without knowing that there's no loss. Finally, when quantum computation principles are understood, it was clear because Toffoli gate is doing unitary transformation, that's why it is reversible. So 70s, engineers came up with fundamental contribution of understanding of information and a very beautiful interpretation of thermodynamics, that information is heat. Each unit of information lost is half kT. So that was the beautiful contribution of engineers in 70s. Then of course Feynman came in and others came in. Now what are these gates? Very simple, Hadamard gate. You take state 0, these are the notations 0 and 1, and it should produce this 0 plus 1. On state 1, it should give you 0 minus 1. What is it? Mathematically, it is very simple. 1 by root 2, 1, 1 minus 1. You can check. It is unitary. U dagger is equal to U universe. And also Hermitian. U dagger is equal to U. Now, there are more general gates. And usually, polymatrices are enough. You don't need more mathematics than polymatrices. Sigma x, which is 1, 1, 0, 1, 1, 0. Sigma y, 0 minus I 0. Sigma z, 1, 0, 1, 1, 0, 1 minus 1. Only thing are the things what you need is them. And you should be familiar with tensor product, direct product. That's all you need. And how to operate these kind of matrices. What is the other one? Now, as I told you, these engineers are so smart that Toffoli came up with this. In a modern language, it is control not. And why am I introducing it all here? Because, this was first discovered by Toffoli to have a reversible logic gate in 70s without really knowing that is quantum mechanics. Now we know in the modern language it is control not. So let me explain to you what is control not. See, for example, then what is control not? So that is what the distable is. It's a more complicated example of that. If, for example, Alice and Bob, if 0, 0, output should be 0. So C here stands for the output. But right down here, I am just saying that the output would be depending on what is the input here. 0, 0 should be 0. 0 again, 0, 0. What is this one? What is the output? Now come to the input. This is the input, this is the output. This, this looks a bit complicated because 3 of them are here. Okay, but if you go to the 2 with 1 control not, you will find out this becomes simple. I'll tell you about that. But the example here is being taken because this was implemented in regular computers, without knowing why it is working, and it was giving rise to reversible logic gate. That was quite unique and quite amazing. Looking at the contribution of the engineers. Engineers are very practical people. So now let me come to the simpler one, control not. In this case, Bob controls Alice. Typically, you will find Alice controls Bob. So the small one is the one which is controlling this big fellow. If this fellow is 0, if this is 0, nothing happens. So 0, 0 remains 0, 0. You see, Bob is controlling. If Bob is 1, you will find out the state will change. You see, Bob is 1. Alice was 0, now it's changed. 1 remains intact. All the first thing is 1. If Bob is 0, nothing will happen. You see, 0 here, 1 here, nothing happens. If Bob is 1, this will again change. 1 change 0. So in the process, Bob does not change, but Alice changes. and you will convince yourself that so-called control knot is the one which is actually unique. It creates entanglement. So Hadamard and control knot are enough. Mathematical, how does it look like? It looks like a 4x4 matrix, which is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0. So basically, if the identity times is poly x is the one. Output is this. You can check it is again unitary matrix, and so therefore reversible. A more complicated version of that was invented by the classical people to show that reversible operations can be done in a classical computer or a classical chip. Basic understanding of that came to us once we came into quantum mechanics. And in the process, we understood the connection of heat and information. Each bit of information cost energy, half kT. That is great contribution, which is experimentally verified. Great contribution of Landauer. So now you can then use this for universal quantum computation. Hadamard control knot. I will not get into details. You guys know more than me. So now algorithms. Varieties of quantum and computers are available. Some of them are depending on this kind of gate architecture, which we have already seen. So by the way, I do not want to hurry. Whatever we cannot cover today, we cover the other day. So the thing is to simply understand the principles of quantum mechanics. Application part is algorithm. So now, there are very many companies which are into the game. So as you might have seen from Google, Microsoft, IBM. See this IBM uses superconducting qubits, and for example, Microsoft had a plan to use the topological Majorana state, which has seen a setback because of experimental problems. Google uses standard, this stuff. Ion Q machine uses ions trapped through light, talking to each other through exchange of light. These people have come up with a simulator. Simulator is a classical machine which depends on like MATLAB, matrix multiplication. Measurement is done through probability. Like for example, you can just like coin tossing. So it can actually simulate what you are doing. If the outcome is good, your program can get into a quantum computer. So you'll find out everybody, IBM has a quantum simulator. First you put your program there, check if it works, then it goes into a quantum computer. So it uses classical statistics plus matrix multiplication. In a regular computer, it is matrix multiplication and quantum statistics. Quantum statistics comes in because, amplitude. So that is the only difference. Now, we have mathematically, people have shown very rigorously that this is universal. You can do anything you want. Now, for example, when you do measurement, the so-called Bell measurement plays a very key role in all of quantum computation. So this I have already narrated to you that this Bell state is the one which is like these two electrons for example, in case of helium atom or hydrogen molecule, the states of electron. So in our physics language, they are actually singlet, up, down, minus, down, up by root 2. Entangled states are up, down, minus, down, up, or plus, down, up by 1 by root 2, two of them. Up, plus, minus, down by root 2, another two of them. 4, why 4? Because the two qubits are making a product state. So 2 times 2 is 4 orthogonal states. These are examples of maximally entangled state. Why maximally entangled? You cannot separate them. Maximality has been proved in a slightly mathematical way that you have to wait through the von Neumann's approach. But what is the state which is two particle but not entangled, separable? Example 0, 0, 0, 1, 1, 0, 1, 1. They are called computational basis. 0, 0 means separable, 0 times 0. If you do a measurement on Alice, which is 0, nothing happens to Bob. Bob stays whatever she has. If it is 0, 0, it will stay 0, 0. If it is 0 plus, stays 0 plus. So measurements of one does not affect the other. Those are separable state. So-called computational basis. Now, Bell states, for example, occur naturally, two of them, singlet and triplet. Others you have to produce experimentally like NMR people did. Okay. Now, spatially separated, some you can be For example, the molecules which people use, NMR people, they're big molecules. So spatial separation is in terms of micro or nano kind of nanometer. But physically, people have now established lines, like for example, Beijing and quantum through these photonic fibers, which are actually huge, like 70, 80 kilometers, even more than that. So there are quantum computational channels which are available, which are in hundreds of kilometers. So those things are now possible. Now you can actually create correlation between distances which are hundreds of miles. Now, Bell measurement is crucial. What is it? It's a two-particle measurement. So this you have to spend a little bit of time, because when you do a measurement, you have to find out, am I doing a single particle measurement or a two-particle measurement or a three-particle measurement? Once that is decided, you have to ask, what are my states? Am I, for example, in terms of a vector in 3 dimension, is it in the IJK basis or R theta phi basis? You have to choose your basis. Then you have to do a projection. So whatever we have learned in classical world, same thing happens here, except here the outcome is arbitrary. So when you do projection along R direction, you find out the component of the vector along radial direction, along theta, along phi, or along IJK, which is XYZ axis. So that kind of mathematics happens here also. So Bell measurement is unique because you have to do measurement in a coordinated basis. You have to imagine yourself that how do it, very tricky. But mathematically it means that the states has to be Bell states, there are 4 of them. So you have to project along those states and outcome would be arbitrary. That is Bell measurement. So this Bell state have provided all the aspects to test principles of quantum mechanics. Many novel things are still coming out. So get yourself a little bit familiar with it and play around. You will still come up with new ideas. How do you create the Bell state? Very simple. Take the states 0, 0. Now you see the architecture like the conventional electronics architecture. Okay. Now Hadamard control node, please work it out. Take Hadamard, it will produce 0 plus 1 by root 2. Control node, which is a 4 by 4 matrix, multiply, you will create the state. I created state which is up, up, plus down, down. Right? If you take state 1 here, it will create minus here, as I see here. This is the triplet state. Now, okay. So more things you can create now. Now, is 2 particle enough? No. We are now into more. So-called very famous GAZ state, Greenberger, Horn, Reidinger. How do you create it? Again, same thing. Hadamard control node. Now, why am I giving this state? Because many properties of this state is still not clear. Beyond 2 particles, it is still unknown. Properties are unknown. What is the measure? What tells you what kind of entanglement they have? What kind of work they can do? They are still matters of research beyond 2 particles. Particularly understanding of entanglement, where mathematics people, physics people can contribute. Application, where engineers and other people can contribute. So these multipartite states are very poorly understood. Okay. Now, what are the tasks? As I told you, quantum random number generation, quantum key distribution, they are the applications of single qubit through measurement. Uniqueness of quantum measurement, the state collapse has been used there. Teleportation is the application of Bell state measurement, entangled state and measurement through entangled state. What happens? You can actually create an unknown state at any point. People have shown even miles across through teleportation using this kind of measurement. So Bell measurement, which is measurement through a coordinated basis, through an entangled basis, can create wonders for you. One wonder is teleportation, which we have seen in Star Wars movies, which is a reality now. Physically, it can create a state at some point, hundreds or 500 kilometers apart. Exact, fidelity 1, exact state will be created. Alif would not know what he has sent. Bob would not know what they have received. But you can actually give a guarantee that it is the same thing which has been sent. You can imagine many physical applications of this kind of thing. People are now, familiar with it. Okay, but it cannot be instantaneous. This is led to very good understanding of foundation. Therefore, you will find that quantum computation has two directions of research. People are still doing foundational aspect, trying to understand what is the physical meaning of information, what is the physical meaning of heat, where is thermodynamics. Of course, that is giving rise to applications like heat engines, refrigerators, but of physical understanding. So foundational aspect and computational aspect of quantum information and is emerging as independent areas of research. Close collaboration is leading to technology. How am I doing time wise? How much time I have? Am I
And
audible?
yes, sir.
Sir,
Yes,
Yes,
sir,
sir.
sir.
5 minutes remaining.
Okay. So what I do is that I will get into this algorithm part a little more carefully day after tomorrow. Now these are the circuit I'm doing for teleportation. Now why am I emphasizing this? Because these are the basic building blocks that will get into implementing algorithms. So please share this file and these notations, get yourself familiarized. Here are the state input goes in. Architecture is very similar to electronics. This arrow stands for measurement. Paramount is the matrix 2 by 2 matrix. Control knot is the one which is a 4 by 4 matrix. This kind of thing is called control X. X is the polymatrix 0, 1, 1, 0. Now Z is the 1, 0, 0, minus 1. So polymatrices, measurement, and electronic circuit. This is what you will see in every architecture. So one half of the quantum computers like IBM, Rigetti, everywhere you will see this architecture, except D waves, which is analog, which will depend on of the so-called annealing, which I had pointed out earlier. So that we will get into later. Know that now it's basically more things. For example, a very simple question you may ask: that if a state is there, how do I know that the state has not been destroyed? So in fact, you can check that without destroying the state. You started with a state, x12, created it. You can check it through this kind of architecture that the state is intact by doing the measurement here and looking at the measurement outcome. This was my first entry into quantum computation through this paper. This was experimentally verified by Professor Anil Kumar in 2010, where we are also co-authors. So now let me not get into principles. There are principles of quantum mechanics which finds applications where, like for example, you cannot create a Xerox of this thing. All that you have to show that unitary matrix cannot create it. So whatever unitary matrix cannot create cannot be done in quantum mechanics. No cloning is an ideal this thing. And this is the new machine about which I'll take a little bit more later. Now let me get into one algorithm, very famous algorithm called DJ algorithm. What is it? Imagine you have a box which you have house with 2 rooms. Now this house is like a black box. These 2 rooms, for example, one room could have a 0, other one 1. So for example, it could have 0, 0. For example, imagine floor height, same floor height is 0, 0. If floor height is little higher, 1, 1. So 0, 1, 1, 0, 1, 1. They are like floor height. So imagine that you have 2 rooms. Then classically, is it possible that only one query you would be able to know it is balanced or non-balanced? Namely, just by one query. Is it 0, 0, 1, 1 or is it 0, 1, 1, 0? 0, 0, 1, 1, imagine is that same floor height. Okay. So whatever language you call. Problem is this, that you have one house with 2 rooms. So if the floor height is same, call it 0, 0. If floor height is high, same but 1 unit higher, call it 1. So it could be that 0, 0, 1, 1, namely floor height is ground floor, 1, 1 is 1 unit of brick in both these rooms. That is one kind class of outcome. Other would be that you see 0, 1 or 1, 0. Either be constant, you see, or balanced. Now, is it possible that one probe, just one query, can tell you is it balanced or constant? That was the thing which was shown classically not possible. DJ algorithm showed that in a quantum computer you can do it. That was the first success. Now, physically, don't worry about the application, how it was done, but what is the idea? Idea is that, imagine you are sending waves. So, for example, if a wave is passing through, if the refractive index is the one which changes because of this 0, 1, 1, 0 or 1, 1, there will be a difference between the left arm and the right arm. That difference can manifest and change the wave function. So therefore, by superposition, you can actually see it. That's what precisely was done. So product state you take, standing for the two arms, one fellow changes, this is the change is here. By superposition, you can actually detect. And nothing more than that. Product state, one fellow changes, like refractive index changing the profile for one light, the other is not changing. And then do superposition and measurement, you get the outcome. So this was the classic one which actually convinced people that quantum mechanics is more powerful. That's the beginning. So I think I'll stop here. Some more algorithms I'll go over next time. Now you may ask questions.
Yes, attendees are requested to ask the queries if they have. Vaishali madam.
Yes, yes. If you have any query, ask to sir.
Yeah, you can actually open your thing and ask me, no problem.
Please unmute and also play the video if you have any query. Yes, anyone is having any doubt, please ask. Yes. Anyone is having doubt? Sir, I think no.
Okay. So I understand that in the beginning it will be like that, but the take-home message is that mathematics is fairly simple. Matrices. The field is beginning, so therefore a lot of people can contribute at each level. Physicists, mathematicians, computer scientists, electrical engineers. There are avenues. Practical realization are just coming in, but quantum computers are available. You can play around, and there are only one aspect you have to keep in mind is measurement. So convince yourself. I'll show you that you can really go to IBM. You can do a search. Go to IBM quantum computer. Maybe we'll share one paper which our colleague people can actually carry it out. So do play around, keeping this measurement aspect in mind. You can actually do miracles. So of some other algorithm, next time I'll explain. Okay, I think then we'll stop here.
Yes, sir.
Yes, sir.
So people can ask me questions, send me by email. Okay, later on I can answer in the next class.
Okay, so I would like to thank you, sir, for your valuable guidance on various topics that you covered today. That is on quantum computer, history of timeline, types of qubit technology, then various concept of superposition, entanglement, quantum gates, types of quantum computer, and circuit for Bell state discrimination also, and no cloning theorem, and various quantum computing algorithm. So this is very helpful to us. So thank you so much, sir, for your guidance.
Thank you. Thank you then. Yeah. Okay.
Yes.
Yeah. Bye.
Thank you very much, sir, for
Thank you.
sharing your valuable time.